All right, here we go. 610 number 7. I've been doing this problem for a long time. Um, the person on a horse used to be called Sir Lost a Lot, which was a pun on Sir Lancelot. So I don't know. Now it's a person on a horse, probably for PC issues now. Um, the other thing that you're going to want to do is they've added a part B, which is actually a really big hint to the problem. Part B asks, how much time is the person on the horse in contact with the bridge after the cable breaks? And the answer is 0 seconds. Okay. Um, Go watch the falling stick video demo I did over in the test prep episodes. And that one, I do a demonstration where instead of putting a lime in a coconut, I put a nail in a lime. And it's a good demonstration to show that parts of the stick are accelerating vertically at a rate higher than 9.8. So the person on the horse or my lime in the demo, they want to accelerate downwards at 9.8. But parts of the stick, because of its angular acceleration, have a linear acceleration that are greater than 9.8 meters per second. So if that happens, then the stick accelerates out from under the falling person and they separate. They're no longer in contact. And then the person on the horse doesn't apply a torque, which is really great, actually. If it did apply a torque, even for any amount of time or for part of the time, this probably would be a lot more difficult. But it's easy to add that extra torque to the end point here, and then you got two torques, and you can go down a rabbit hole and never know why you're wrong. So conceptually, you got to get over that part where the bridge and the horse separate, and then therefore cannot apply a torque to the bridge and does not affect its motion after the cable breaks. So once you're good on that, the only torque is from the weight of the bridge itself acting vertically. So since it's at a 20-degree angle, we've got to find the perpendicular component. It's a cross product. So we're going to go with our mg cosine 20 and then times L over 2 since it's acting at the center of mass. Okay, so there's your sum of torques. Since it's a stick rotating at its endpoint, its moment of inertia is 1/3 ml squared, where the L is the whole length of the stick, and then times angular acceleration. One step of algebra, and we can get the angular acceleration 3g cosine 20 over 2L. Boom. Okay, so that part's not so bad once you realize that other torque doesn't exist. All right, what are we doing next? Boom, boom, right? Okay, so that part asks us about acceleration. Also keep in mind the acceleration was a function of theta, right? We had to put in that 20 degrees. So as that 20 degrees changes and the stick falls, the torque will also change, which means the angular acceleration would change, which means we should try to use energy, right? Anytime you find an acceleration not being a constant rate, you should try to do other parts using energy, especially any parts that's asking you to find velocity, final velocities. So two big clues to use energy approach. They're asking you for a final velocity or a final height, and the acceleration's not constant throughout that process. Okay, so if those two things are happening, try energy first, right? So then what do we got going on here? We got our stick. It's starting at 20 degrees above the horizontal. It swings down and hits the vertical wall of the castle, and they ask us for the final velocity that it strikes the castle wall with. So what we're going to do is we're going to start out with some potential energy from gravity. We're going to track that height of the center of mass. That's going to be the height we're going to use for our MGH. So the center of mass starts 20 degrees above the horizontal, which means to get to the horizontal, it falls L over 2 sine 20, that top little distance there. And then it falls down another L over 2 as it reaches the vertical. So our height, or our change in height, is L over 2 plus L over 2 sine 20. We're going to use that height for our MGH. And then we're going to use rotational kinetic energy as our final type of energy. There's no other types here. And so we got 1/2 I omega squared, where moment of inertia of a stick rotating around its endpoint is 1/3 ml squared, right? And then we have our final velocity squared. And from that, you can solve for the final velocity. Okay. So energy approach, right? Those are the key steps on that one. Energy approach if you're being asked about final velocity, or if the acceleration isn't constant through the motion you're looking at. All right. So then they come back and they ask us about accelerations and hinge forces. Hinge forces are kind of tricky because the easiest way to do it is to find their components and then put them together if they ask you to. So that means figuring out the acceleration horizontally. Also keeping really big in mind that when we do Newton's second law, sum of forces equals ma, that only applies to the center of mass. It doesn't apply to any other part of the object, only the center of mass, which means we need to know the accelerations of the center of mass. So that's the first step. In part D here, we need to find the tangential acceleration, which is then going to be alpha times L over 2. We already found angular acceleration in the first part, so we've got that. That gives our tangential acceleration. Now, the other thing to keep in mind is there might be a centripetal or a radial acceleration once it's in motion, and we'll have to do that in part E when it hits the wall and it's in it has a final velocity. But in the initial conditions, its angular velocity and all the parts has no velocity, so it can't have a centripetal acceleration yet. Remember, centripetal acceleration is the rate at which it's turning. So if it's not moving yet, it can't be turning yet. And we covered that quite a bit way back in our two-dimensional motion unit, right? Acceleration should be thought of as two parts: a turning part, which is the radial part or the centripetal part, and a speedy up part, which is your tangential part or your parallel to the velocity part. So here we do have a tangential part because it has an angular acceleration, which we can find. Boom, boom, tangential acceleration right there. But it doesn't have a radial component. So that makes this a lot easier. If it had, we've done problems in the past where it had both, and we'd have to add those together vectorially and find the acceleration and then find the x and y components of the total acceleration. Here we don't have that centripetal acceleration, so that makes it a little easier than some things we've done in the past. Even though this problem is very comprehensive, bringing up lots of topics from throughout the whole year. So what does that mean? So since we have a tangential acceleration, which I've drawn here in this lower diagram, right? This diagram is more about forces, this one's about the accelerations. So we have our tangential acceleration, and I got to break that up into an x and a y component so I can find the hinge forces, horizontal and vertical components. Excuse me. So what do we got going? We've got then our horizontal component is alpha over 2, right? This is your tangential, and then we're just breaking that tangential piece into our horizontal and our vertical components. So using alpha from part A, whatever that is, and whatever your L is, divide that by 2, and then find the appropriate horizontal and vertical components of your acceleration using the initial 20 degrees from the vertical. Right? Then, once you have your horizontal and your vertical components, you can sum up your forces horizontally and vertically. Right? So there is only one horizontal force from the hinge. Right? So it's just max. So if you got your x acceleration here, you can easily find the hinge force by multiplying by mass. You do have two forces acting in the y direction, right? This thing still has weight. So we do have our hinge force vertically here minus our vertical weight force there, and that'll equal our vertical acceleration AY, which we found from breaking that tangential acceleration into its parts. There's a lot going on here, so if you're confused, you're probably not the only one. Email me follow-up questions. All right, part E then, once they want the hinge forces when it gets to the vertical. And there's a lot going on here. There's a lot going on in my diagram. I tried to color code it the best I could. I got velocities here in blue, I got accelerations here in red, and I got my forces here in purple. Purple doesn't seem to be showing up. Maybe it'll show up better later. So again, since it's in the vertical position here, boom, boom, when the vertical position, the weight force is down vertical from our hinge point and is parallel to the lever arm. So the torque here is 0. The torque has gone to 0, right? We kind of have, the stick goes through some process. There's no torque when it's completely vertical here. The torque increases to a maximum where the weight force becomes completely perpendicular to the stick. So this is where our acceleration is max. And then it gets again to the vertical where our mg and our lever arm are parallel, and the acceleration, angular acceleration, again goes to 0 because the torque is 0. There's no cross product components to find. Everything's parallel in the vertical positions. So sum of torques is 0. because the force of the weight is vertical, which means there's no angular acceleration, which means there's no tangential acceleration. Just like in part D, there was no centripetal acceleration. Here, there's no tangential acceleration, except now there is a centripetal or a radial acceleration from the hinge. And we can find that using our answer from part C, knowing the final angular speed. So this thing is accelerating, right? There's no tangential acceleration, but it is about to go from moving down to moving up. And so we do have a vertical centripetal acceleration pointing upwards. And we can find that using good old v squared over r. The other thing is you got to find the tangential velocity of the center of mass. Again, this equation is only working for positions where you choose r to be. And what we want is, if we're going to sum up the forces, Newton's second law only tells us about acceleration of center of mass. So we're going to need the velocity at the center of mass. So we're putting in omega r, boom, boom, to find that velocity. That simplifies the centripetal acceleration down to omega squared r, and we're going to pick r to be L over 2 because we need the acceleration at the center of mass. All right. Deep breath there. So then now we got to find our forces. So sum of forces in the x is 0 because there's no acceleration tangential to the stick, which is the horizontal direction. So there is no horizontal component from the hinge. All the hinge needs to do is pull up, but it's got to pull up more than the weight so that we can get that center mass to keep going up. Much like a thing at the bottom of a loop-de-loop or at the bottom of a pendulum, something like that. That all our forces now are aligned along the radius, and so when we're going to add up our forces in the y, we have our hinge force up positive. I know it's got to be positive because it's towards the center of the rotation, and then we got our weight force down negative because down and away from the center of the rotation, and then we're going to set that equal to ma(y), where the y acceleration is the centripetal acceleration. So solving for our hinge force, we've got our mass times our vertical acceleration or our centripetal acceleration, omega squared L over 2, plus then the weight force to solve for the hinge, because that hinge has to be pulling up more than the weight. All right? That's a tough one. If you walk through this one and you really feel like you understand all the steps and you think you could do something like this on your own, you're really on your way to kind of really getting the rotational unit down and bringing back a lot of concepts from earlier in the year about circular motion. So if this is making sense to you, you are on the right track. If you're not, don't worry, you're not the only one. This is a weird problem. There's so many concepts that tie together subtly that it's easy to kind of get lost in the complexity of how subtle the different pieces come together. So email me some questions if this one's still confusing you.